All right, let's dive deep into the solar inverter. This session is all about Chapter 2 of the Eco-Egypt PV training program, book and slides, and we are going to discover the true brain of any solar power plant. You know, when we look out at those massive fields of solar panels, it's really easy to think they're doing all the heavy lifting. But the truth is, without the inverter, all that captured sunshine is completely useless to our modern electrical grid. So, in this explainer, we're going to get into the details of the engineering, the specifications, and the sheer operational intelligence of these incredible machines. Here's the blueprint for today's explainer. We'll start with the DC to AC translation, unpack those complex engineering specs, compare string versus central units, look at hybrids and off-grid setups, and then finish up with smart operations and plant protection. Section 1. The DC to AC translator. Bridging the electrical language gap. So, you might be wondering, how does a solar panel actually talk to the electrical grid? Because that is the fundamental problem right there. Solar panels and the grid speak completely different electrical languages. Solar panels generate power in a straight line, as direct current, while our homes, businesses, and power grids operate on alternating current, power that constantly fluctuates. If you tried to connect them directly, absolutely nothing would work. It'd be a catastrophic misunderstanding. Enter the inverter. This device acts as that essential bridge, taking the raw DC power output and smoothing it out into the usable AC power that our world literally runs on. Without this conversion process, every single watt of solar power generated by those vast arrays would just be trapped there. It's actually kind of wild and honestly a little terrifying that early 6-step inverters produced waveforms so rough and jagged, they literally caused appliances to overheat and lose power before PWM technology came along to save the day. See, early inverters used just 6 diodes, which created these sudden, blocky voltage changes. But today, modern pulse width modulation, or PWM, compares the DC input with grid feedback thousands of times a second. The result is a beautifully smooth, highly efficient AC wave. It's a real game changer. Moving on to Section 2, Unpacking Inverter Specifications. Let's dig into the translator's dictionary using the Eco-Egypt engineering standards. When engineers look at these machines, they neatly separate what the inverter absorbs on the panel side versus what it delivers out to the grid side. On the DC input side, you've got the max voltage, which dictates exactly how many panels you can string together safely. Then there's the MPPT, or maximum power point tracking range. That is the sweet spot where the inverter operates at peak efficiency. Flip over to the AC output side, and we're looking at max power and the power factor, which the inverter can actively adjust to make sure the local power grid stays nice and stable. Okay, let's talk math for a second. To calculate the total inverter efficiency, it's a 2-part process. You have to multiply the tracking efficiency of the MPPT by the actual DC to AC conversion efficiency. First, you measure how well the inverter tracks the shifting voltage from the panels as the sun moves across the sky. That's your tracking efficiency. Second, you measure how well it converts that captured DC into AC. Multiply those two together, and boom, you get your true overall rating. And this number right here brilliantly illustrates the sheer performance of modern units. They routinely hit 98.5% efficiency or even higher. That means almost no power is lost in translation. To put that into perspective, for every 100 watts of raw solar energy pouring into this machine, 98.5 watts are successfully pushed out to the grid. That is just an astonishing feat of modern power electronics. But hey, it's not all just internal math, right? The physical specs are absolutely crucial. Think about an IP66 reading. That's the heavy-duty environmental protection that allows these machines to survive the intense dust and heat of places like the Egyptian desert. These units generate serious internal heat while handling massive voltages, so their sealed enclosures and advanced ventilation systems are every bit as important as the circuits inside them. Section 3. String versus central inverters. It's all about scaling the solution. So depending on the scale of your plan, you basically have 2 choices. You've got string inverters, which are modular setups usually mounted right near the solar arrays. They're highly flexible, and if one happens to fail, you only lose a small, localized section of your output. They're perfect for commercial and industrial sites. On the flip side, you have central inverters. These are massive, shipping container-sized behemoths handling up to 9 megavolt amps. They need their own dedicated central rooms, but they give you a much lower cost per watt, making them the go-to for huge utility plants over 1 megawatt. When we analyze real-world industrial units from the training material, like the Huawei Sun 2000, we can see exactly how these specs, like a 1500 max DC voltage, play out in action. A 330 kVA string inverter, for instance, utilizes 10 separate MPPT inputs. That means it can independently optimize 10 different pairs of solar strings at the exact same time, seamlessly adjusting to shifting cloud cover across the field in real time. Section 4. Hybrids, off-grid, and pumps, exploring the different dialects of power. Way beyond standard grid-tied setups, inverters have to speak different dialects depending on the specific job. A hybrid or power conversion system is bidirectional. It can charge battery storage and push power back to the grid simultaneously. Off-grid inverters, on the other hand, are high-maintenance, isolated islands of power where utility connection is totally optional. And then you have solar pumping inverters, which are fascinating. They use a variable frequency drive to soft-start heavy agricultural water pumps the second the morning sun hits the panels, following the irradiance directly and completely eliminating the need for expensive battery banks. Just think about the sheer complexity of a high-maintenance off-grid system for a moment. You're dealing with battery banks, charge controllers, and intense load management just to keep the lights on. Now contrast that with the direct AC motor connection of a solar pump. The pump inverter acts as a direct, seamless bridge from the solar array straight down into a submersible pump's motor. It's incredibly elegant, incredibly cost-effective, and just a brilliant engineering solution. Finally, Section 5. Smart Operations and Protection, the nervous system of the plant. These 5 split-second operational steps are exactly how the inverter safely introduces solar power to an active, buzzing electrical grid. It doesn't just blindly dump power. After finding the maximum power point, it acts more like a super cautious driver pulling into a busy intersection, carefully checking the grid's voltage and that 50 Hz frequency signal. Only when it confirms absolute stability does it synchronize and smoothly merge its power onto the grid. Now, what happens if that grid suddenly just dies? Say there's a blackout. That's where anti-islanding protection instantly kicks in to stop exporting power. Think about it. If a neighborhood loses power, utility workers are sent out to fix dead wires. If your solar inverter just kept pumping out 400 volts into those supposedly dead lines, it would be absolutely lethal. So using active frequency drift and passive voltage monitoring, the inverter detects the outage and completely shuts down its output in milliseconds,